Hey everyone, today I'll be going over Leetcode 701, insert into a binary search tree. So they have all this, but really all it is we're given some binary search tree, they give us a value and we have to insert it, then return that tree after we've inserted it. So I'm going to delete all this. So really this problem does require kind of some fundamental knowledge about a binary search tree, but in brief, a binary search tree basically means that at any given node, all the values to the left are guaranteed to be smaller, and all the values to the right are guaranteed to be bigger. Some have it greater or equal or less than equal, but yeah, all to the left is less, all to the right is right. And we can look at these trees here. You'll see the 7 is greater, these are smaller. So at any given node, so at 4, 2, 3, and 1 are smaller. At 2, 1 is smaller, 3 is bigger, etc., etc. So to insert a tree, or to insert a value into a tree, say we're given this here, this tree here, and we wanted to insert a 5. Is it greater or smaller than 4? It's greater, so we go to the right. Is it greater or smaller than 7? Well, it's smaller, so we go to the left. And there's the 5 right there, actually. So it just follows that logic. And literally, as you're saying it out loud, you realize that it's actually pretty easy to do recursively. So we're given some root, and basically we have to return this root after we've inserted this value. So really all we do is we need to basically just keep bubbling through the tree as so long as we find a place to put it. And how do we know where we insert it? Well, it's just the null point. So basically, if we go back to this example and we're inserting this 5, we'll go here, or we'll go here, then here, and it'll be null here, so we'll insert it there, and you can look, that's exactly where we put it. So basically, you just follow the logic, go left or right based on what we've seen, and then insert it at the null point. So how we do this is we're going to do this recursively, right? And the base case is, what did I say? It's when it's null. So if root is equal to null, then all we do is return a new tree node with the value we're trying to do. So we create a new node for that value and we insert it because we're now null. And the proof why this works is, say we're given an empty tree, no nodes in the tree. Well, whatever value we pass is going to be the new root. So root will be null and we'll just return this new one and that'll be the tree. If not, we have to find a place to put it. So at this current node, what did I say? So all to the left are smaller, all to the right are bigger. So basically we have to check that. So if this value is smaller than this current node, and we'll do less than or equal to, different people have different preferences, but so less than or equal to here. So basically if val is less than or equal to root.value, that means that we have to insert left, basically. And we have to modify this tree. So let's go root.left is equal to, and let's take this, and we're just going to keep bubbling through, and we're going to start searching left for a place to put it, because it's eventually going to hit this root equals null base case. So we start building on the left. Else, that would mean that it was bigger, right? So let's copy this, and we're going to have to search right at this point, and we'll do that to the right. And then if we get down here, we're just going to return root. Now, why do we do that? And why did we do this up here? Well, it's because we built left and right. So at this point, we're going to assume it recursively built it. It found a place to put it. Now we have to return the root because this is the node at this point. And then when we hit this base case, we're just going to return the fresh node at this point. So like this right here is essentially like this little blue piece right here where it inserted the 5. So let's run this. It looks like it's pretty good. Let's submit it. And yeah, 100%. So let's talk about time and space. So it's a little tricky, and I'll explain how it works. So space is just going to be, so people are picky about this. If you actually want to count the recursive call stack as space, it's technically log n, because that's actually the max amount of recursive calls we have to make. And recursive calls, those functions actually take up space in memory, so we call it that. It doesn't really use like any arrays or anything, or any data structure. So it's, some people call it O1, I call it log n because of the recursive call stack, but it is what it is. So time will also be log n for that same exact reason. Now I say log n, and it's not n log n, it's just log n, and it's not n because of this logic here. So we're actually decreasing the search space every single time. And basically we're cutting the search space in half every single time we insert it. Now, what I mean by that is, say we had some massive tree and we're finding a place to put it. Well, it can either go left and right at any point. So if we choose that decision left, we've cut out half the tree. It can't be in the right side. So we've cut out half of the search space. And we do that, we have it every single time. So because we're having it, it's actually log n, and log n is less than n. It's actually very good, it's a very desirable time complexity. So that's space and time, and hope that made sense. Thank you.